What we've been talking about so far with exponent rules are these three rules that we've got here. These are the official algebraic ways of keeping track of the patterns, where a represents the base of an exponent, so you'll see that I have a to the n here. A is the base. It can be a number or a variable or a combination where we have however many times that number shows up. N means however many times. Then you got the base to that number of exponent. This rule here is when I have two different things multiplied together that have the same base, I add their exponents. Let me just put that in, I'm going to add their exponents there. Then here, when I have a base to a power, and that whole thing then becomes the base to another power, I multiply the exponents. And then if my base has two different parts to a power, then each of those becomes its own individual base to those powers. Again, this is everything that we've been looking at so far. I just want to give you a pattern or maybe something that you could write right at the top of your paper when you're looking through problems. So let's look at each of these individually. Alright, so we're just looking at this first rule here where you've got anything multiplied together, basically definition of exponent. So this is the same as when you have 2 times 2 times 2 equals 2 to the third power, right? And this is something that I feel like you all know, and you've been pretty proficient at going in this direction. What I noticed though on our quiz is that you're not well practiced yet at identifying what the base of any given exponent is, or what is it that's getting repeated all these times, right? So what I want you to do is look at the next several problems, pause the video, and identify the base. Then check to see if you identified the correct base. So again, I want you to identify the base of each of these, and then play the video again and see if your bases are correct. Now, if you can identify the base, it'll alleviate some of the confusion that we have about when an answer is positive or negative. For example, the problems that look like this are often confused with problems that look like this, negative 2 to the fourth. Whereas here, the base is whatever is inside the parentheses there, and here the base is just the 2 right here. The other way that this could be written is negative 1 times 2 to the fourth, which then makes this expression look like this expression, where you have two numbers multiplied together, where only one of them is the base of the exponent. So what you'll notice about this rule here, this is another rule, is that you've got the same base, and when you have the same base, that means you can just multiply these exponents up here. You add the exponents. So what this looks like, or the short form of it, is if you have something like x to the second times x to the fifth. Well, what this actually means is x times x coming from the x squared, and 5 different x's multiplied together coming from the x to the fifth. In other words, we're using the definition from the previous slide to help us figure out what the answer to this kind of multiplication is going to be. And if I use definition of exponent, I see that I've got 7 different x's here, so that means the total then is going to be x to the 7th. The shortcut to that, or the flexibility of thinking, is seeing that I'm just adding these two exponents together. But I don't want to look at this shortcut and sacrifice seeing how this rule is connected to the rule we just looked at. So when I'm given a problem that looks like this, an example problem, what I'm going to do first is use what I just practiced and identify the base of each of these exponents. So I'm going to say that 2, the base on this exponent of 2 is an n, and the base on this exponent of 4 is also an n. What I also recognize is that I've got multiplication here. Whenever there's an operation that isn't identified, it's multiplication. So what that means is I can flip the order around of all of these things. So in other words, I can put this 3 and a 4 together here. It's 3 times 4. And then I can also take these two bases of n with their exponents, put those together. So I've got n to the second, n to the fourth. And so when I simplify this all together, I get 12n to the sixth. Now from here, what I can also do is look at this term, and I can recognize it's part of the polynomial series, right? And this term is a monomial with a degree of 6, right? So if I were to write this out or name this, this would be a 6th degree monomial. In other words, this rule that we're working with right now is not only connected to the definition of exponent, it's also directly connected to naming a polynomial by degree and by number of terms. Now this final rule that we've been looking at is called the power rule. Power because we've got a base to an exponent to another power. And the shortcut rule for this is just to multiply those two exponents together. Now the reason that this is happening is if we had, for example, let's say we've got x to the third to the fifth power here. What this means is, if I look at order of operations, or even my base identifying skills, when I have this 3, this exponent of 3, the base on the 3 is just the x right here. The base on this exponent of 5 is the entire parentheses. So what I'm going to do is I'm going to look at this outer parentheses, this 5, and write it out. And realize that I've got an x to the third in each of those. So in other words, I've got this parentheses that happens 5 different times. Right, by definition of exponent. And then inside, I've got x to the third, which is just this, right? So once this is all said and done, I've got 3, 6, 9, 12, 15, or x to the 15th, which is the same as 3 times 5. Again, this line right here is showing how this rule is connected to the other rules that we've been talking about so far. But over time, it makes sense to learn the rule specifically, or the shortcut, to save time as we're working through more complicated problems. Since this is a discrete or an individual skill all by itself, and we're using it as a part of larger problems. Another rule that we look at is when we've got one base on the exponent of m, but inside that base are two separate parts, or more than two separate parts, multiple parts. When that's the case, I take the m and it becomes the exponent on each of these. In other words, it follows this rule up here, but it happens 2 different times. So let's look at what that looks like. So we might get a problem that looks like 2x to the third. So again, using my base identification, I see that the base on the 3 is this entire 2x. So if I'm following the exponent rule, the definition of exponent, I've got this parentheses thing happening 3 separate times because of the exponent of 3. And then inside, I've got 2x, 2x, and 2x, which, when I use the commutative property, means I can rearrange all of these. So what I've really got here is 2 to the third power, and I've got x to the third power, right? Which is just showing here then that I can take this exponent and put it on this new base and on this new base. So 2 to the third, x to the third. So I might have an example that looks a little bit more complicated, something like this. And so what I'm going to notice is that I've got 1, 2, 3 parts of my whole base. So this parentheses is the base on the 3, and it's got 3 individual parts. So I'm going to apply this rule where the exponent goes to each of the individual parts. So in slow motion, that would look like this. It would look like this, where I took the exponent and put it on each of the bases. Notice I put each of the bases in parentheses, so that allowed me to keep this -3 together, x squared and x to the 5th together. And so now what I can do, now that I've taken this power here to each of the new bases, I can use this rule to simplify. In other words, I can take the exponent in the middle and multiply it by the exponent on the outside of the parentheses. So then what that means I've got is 3 to the third power, -3 to the third power becomes -27. 2 times 3 becomes x to the 6th, and 5 times 3 becomes y to the 15th. Now I'm going to use this for a second as a way to look at an entire term. So this is still just one term, one monomial. There's no addition or subtraction or division to separate this into different parts. And so I'm going to find the degree of this monomial together. So first I'm going to just name it monomial. That's its last name. And when I'm looking at a monomial, I'm going to determine the degree by assessing all of the exponents together. So these exponents here, these two exponents, have different bases. So as far as simplifying what this term actually is, this is the end. However, the degree of this whole thing is going to be these two added together, as if there were the same base. And so the degree of this entire thing then is going to be 21. So this is a 21st degree monomial.